Hi everyone. In today's lesson, we're going to be starting a brand new unit and it's all going to be on transformations. So hopefully in your introduction video, you kind of have an idea of the different types of rigid transformations that we're going to be learning today. So figures in a plane can be reflected, rotated, or translated to produce new figures. The new figure is called the image, and the original figure is called the pre-image. The operation that maps or moves the pre-image onto the image is called a transformation. And you guys kind of got the idea what some of those are from the video that you watched earlier. You have reflections, which are your mirror images, your rotations, which are your turns, and your translations, which are your slides. So when you name an image, you take the corresponding point of the pre-image and add the prime symbol. So for example, and this is really important for notation, if the pre-image is point C, then the image is C prime, and that's how we note it. And it's read as, like I said, C prime. So what you do is you take the letter and you put a little apostrophe at the end of it to note that there was some type of change to it. So let's take a look, guys, at how we're going to name some of our transformations. So if you take a look at triangle ABC, and then we can see the new one with the A prime, B prime, and C prime. So this is our original here as ABC. And then the new one with the prime marks, A prime, B prime, and C prime. I'm going to note here in blue. Okay, so the new figure is the image that I just noted here in blue. We're going to name and describe the transformation. Well, if you take a look, if I started at point A and I kind of went, it doesn't look like I made that mirror image to do a reflection. It doesn't look like I turned to do a rotation. So it has to be the slide. So we're going to say a transformation or a translation. And to be specific, let's take a look at point A. And let's count up and over how many units we actually went. So if I would slide up 2 units, I would get it on the same level as A prime. So we're going to say up 2, and then to the right, 1, 2, 3, 4, 5, 6 units right. Okay, for part B, it says to name the coordinates of the vertices of the image. So again, image means the new one. So the new one that I have in blue. So for A prime, what's our coordinates? It'd be 1, 3. For B prime, it's 4, 7. And for C prime, it's 4, 3. Okay, and then finally, when we take a look at part C, is triangle ABC congruent to its image? You're going to find that when we have any type of translation, rotation, or reflection, that yes, it would be congruent to its original image. So that would mean if I picked up A prime, B prime, C prime's triangle and put it right on top of the red triangle, it's going to be exactly the same size and shape. So we're going to say yes. And how could I show that? I could show you guys too, but we, just for our time's sake, you could just write that I could show you by side, 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 right? If I actually counted up the blocks on each one of those, so in this right triangle, I could show you with the distance formula, or I could show you with Pythagorean theorem, the lengths of AB and A prime, B prime to show you that those are the same lengths. I could show you just by counting with AC and BC that they'd be the same lengths as A prime, C prime, and B prime, C prime. But I think you guys trust me on that one. Those are all going to be the same. All right, so guys, we're going to take a look at these ones as well. We want to name and describe the transformation and then determine is triangle ABC congruent to its image. All right, so remember, image is the new one. So I'm taking a look. Here's ABC down here, so the pre-image. And the image is the new one, so A prime, B prime, and C prime. So we're going to go through our different types. So we have our possibility of a reflection, because to me, this looks like I have a mirror image happening. So this would be a reflection. Now, what specific type of reflection could this be? Well, reflections usually occur across lines or axes. In this particular case, if I were to draw a line, and your line of reflection has to be equidistant from each one of those points. So if I drew a line right here in green, you can see that from A to that line and from A prime to that line, you can see that I have 1 unit. Same here from A prime, it's 1 unit across. If I go from C, do you see how it's 2 units? C prime would also be 2 units to get there, okay? So that's how we can make our line of reflection. It's sort of the midpoint whenever you have between those 2 points. So I'm going to write that down. So if I connected C and C prime and found the midpoint, that would give me a nice place right there of where I could find that line of reflection. So our line of reflection in this particular problem happens to be the x-axis. Okay, and then is triangle ABC congruent to its image? It most certainly is. Okay, let's take a look at question number 2. So again, I'm looking at the pre-image ABC and looking to see what was done to it to get to A prime, B prime, C prime. To me, it does not look like it was reflected this time because of where the point locations are. It does not look like it was picked up, down, left, or right to get there either. So this time it looks like it was turned to get there. So any type of turn that we were mentioning is going to be called a rotation. You're going to learn in a lesson in the future how you're going to specifically get to the points in a rotation. But for right now, all I want you to know is that each quadrant represents 90 degrees. So if I move from the third quadrant to the first quadrant, that would be 2 quadrants of movement. So if each quadrant is 90 degrees, that means that I would have 90 plus 90, so that would be 180 degrees in terms of the movement of the turn. So we would say this was a 180-degree rotation about the origin. You can see movements of quarter turns. Those would be called 90-degree movements. They could be clockwise or counterclockwise. Counterclockwise would be moving backwards. Clockwise would be moving forwards. For a 180, it doesn't really matter which way, because if I move 2 quadrants forward or 2 quadrants backwards, I'm still going to end up in the same location. Okay? All right, next. The next thing we're going to be talking about is something that's called an isometry. An isometry is a transformation that preserves length. Isometries preserve angle measures, parallel lines, and distance between points. Transformations that are isometries are called rigid transformations. And the word rigid means that you can't move something, okay? So if you have something that's considered to be rigid, you can't bend it, you can't break it, you can't stretch it. So that means that the type of transformations that we're going to be limited to would be our reflections, our rotations, and our translations, our slides. Okay, so for A, B, and C, for example, 2, does the transformation appear to be an isometry, meaning does it preserve length? Okay, well, if I take a look at A, if I would start out with the darker figure and move to the lighter figure, it looks like it was stretched, right? And it doesn't appear to be congruent. So we're going to say, no, it's not congruent. For part B, if we would move from the gray shape to the white shape, it looks like we have a turn. So because we're dealing with some kind of rotation, and it also looks like the shapes appear to be congruent, we would say yes, that we have isometry. And then for part C, since we look like we're just picking that shape up and sliding it around, this looks like a translation. It also looks like the shape appears to be about the same in length. We would say yes, that this would appear to be an isometry. Okay, so since an isometry preserves length and angle measures, we want to apply this now to a more specific shape. So in the diagram, triangle JKL is mapped onto triangle MNP. The mapping is a reflection. Given that triangle JKL is mapped onto triangle MNP is an isometry. Find the length of NP and the measure of angle M. Okay, this is telling you specific order, and it's also telling you, remember how before we had those congruent statements? It's also telling you which angles match up with which angles. It's also telling you what side lengths match up with what side lengths. So if we know like that J is in the first position, it's going to map up with M, which is in the first position in the other triangle. See how we have our letters right here? J and M. And that's one of the things that we actually have to find, right? Eventually. But just to illustrate that further, K is mapped up with N, and L is mapped up with P. Okay? If we're talking about anything further, we would know another thing. If we need to find NP, let's look here. NP is the last two over here. So on the first triangle, it has to be KL. Well, if I'm looking at triangle KL, I know the length of that one over here. Triangle KL is equal to 9. So therefore, it has to equal the same thing on NP, because when we have a rotation is an isometry. So because we have an isometry, it's going to preserve any type of angles or any type of length. So we would say that KL and NP are going to equal one another. So we're going to say that NP is going to equal 9. Okay, the next thing that you were asked to do is to find the measurement of angle M. Well, the measurement of angle M has to measure the measurement of angle J. We know the measurement of angle J equals 48 degrees. So, oops, right here. So therefore, the measurement of angle M also has to equal 48 degrees. So again, because we had a rotation, we can make those angle relationships and side lengths be equal to one another. All right, so let's try to wrap this lesson up. If you take a look at these two questions, we're going to first determine, does this appear to be an isometry? And then to explain yes or what, tell me why or why not. And then in question number 4, it's given to you that triangle ABC is mapped onto triangle XYZ, and it's an isometry. That's important. we're going to find the length of XZ and the measurement of angle Y. So take some time right now, pause your video, and see if you can come up with those two answers. All right, so see if you guys got those right. Number 3, the answer is yes, because we had a translation, and translations are going to be a rigid transformation, so therefore they're going to preserve length. For question number 4, we have that the correct answer for XZ is going to be 17. How I got that was we know that XZ is going to be the same thing as AC, and we get that from that mapping statement. AC and XZ would be in the same positions. I know that AC is 17, so therefore XZ would also have to be 17. I know also that the measurement of angle B would have to be the same as the measurement of angle Y because they're in the same positions. To get that measurement, I know a lot of facts based on that triangle ABC down at the bottom. So I know triangles adds up to 180 degrees. So if I did 180 minus 36 minus 54, I'm going to get 90. So if I know the measurement of angle B equals 90 degrees, I also know that the measurement of angle Y equals 90 degrees because we have an isometry.